So I'd like to start by thanking the organizers for giving me the opportunity to speak at this very nice workshop. So today I'm going to talk about dimensionality reduction of SDPs through sketching. This is joint work with Andreas Blum, who is sitting here in the audience and will stay here for the rest of the semester. So if you also want to discuss this with him, please do. And Andreas, if I say something which is too wrong, interrupt me. You find a paper on the archive with the same title as this talk, where you find more details about what I'm going to talk about now. Okay, so as the title already says, we're going to talk about SDPs here, so semi-definite programs, and they are optimization problems of this form. So you have some matrices BI, which are symmetric, and which define your constraints, and some matrix A, which defines your target functional, and you want to optimize over all positive semi-definite matrices which satisfy these constraints, and you want to optimize this target functional. And they are sort of a generalization of linear programs, and they provide a natural framework for many optimization problems in quantum information theory. So they have really many applications throughout quantum information theory. And there are many equivalent forms of writing down an SDP. So maybe your favorite SDP does not look like that. You had maybe something different in mind when you were thinking about an SDP, but every SDP can be written in this way. And they also have a rich duality theory. And we also have similar results to what I'm going to talk about for linear matrix inequality feasibility problems, which is somehow the dual picture to this sort of problem. But I'm not going to talk about this. So if you're interested in that, please take a look at our paper. And I must also warn you that I will be a little bit sloppy when it comes to whether I'm talking about real matrices or complex matrices, but this doesn't really matter. So maybe some constant here and there is different, but there is no big difference whether we're talking about complex or real matrices here. Okay, and I should also say that I will call SDPs, which are given in this form, sketchable SDPs. Okay, so what's the good news about SDPs? Most of them can be solved in polynomial time. So for instance, if you take the ellipsoid method, which is not what you would use in practice, you can prove that you can solve them in this time. So D here is the dimension, big D here is always the dimension of your matrices. M is the number of constraints you have, and this is the precision you want. So so you can see it's polynomial, but it has a bad scaling. And we have seen already yesterday in the talk that when they wanted to compute, for instance, the diamond norm, they could not go beyond dimension 20. So the bad news is that in practice, you quickly run out of memory when you try to solve large instances of SDPs, and it takes ages. So as like yesterday, 20. So if you look at simpler SDPs than computing the diamond norm, I can go up to dimension around 1,000 with my laptop, but not much beyond that. And so we need new techniques to solve large instances of these problems for this to be practical. And it would be very nice also if we could use current solvers. So if you could just take your favorite SDP solver and use it to solve larger instances of SDPs. So while we were working on this, there has been other work in this direction. So just to mention one, there's a paper by Trapp and others called sketchy decisions, in which they also do something similar to what we do here. However, I should say that they use non-linear methods, and they also need a new solver to apply their methods to, and it only applies to a specific class of SDPs. Okay. So what's the idea here? So we will take some positive linear map such that if we apply it to the matrices that define our constraints and some optimal point of our SDP, with high probability we will somehow preserve the Hilbert-Schmidt scalar product between these guys. So, and we also want, why do we also want it to be positive? Well, so that we somehow preserve the feasibility set. So the first, demanding that this is the same and is essentially the same and is also positive is telling us that, you know, we are somehow preserving the feasibility of this optimal point x star. And then if this output dimension here, small d, is smaller than d, we will then can define a smaller SDP with our phi bi's. And this is where the sketch comes from in the title. So we will refer to these guys here as the sketches because they supposedly preserve the essential features of your constraints but are smaller or simpler. And we hope that by solving the SDP we get from these smaller matrices, we can still say something about the value of the original problem. And as I said, if this D is smaller than the original D, and computing these matrices phi of BI is not too expensive, then we'll get a computational advantage, and we will also need much less memory to solve it, because again, we have a smaller D. Okay, so now the first no-go theorem, this doesn't work. So if you want this to work for all SDPs, we can show that the output dimension has to be of the same order as your input dimension. Even if you don't want this map phi there to be positive, just linear. Why is that? Well, in 2014, Woodruff showed that the same result for the operator norm. So if you want to, if I give you a matrix and then you want to get like a sketch of that matrix and you want to say something about the operator norm of that matrix, then you can only do this if the smaller matrix has essentially the same order, is the same size as the original matrix. And you can formulate the operator norm as an SDP. So this problem is clearly included in the larger problem of sketching SDPs, and we cannot do this in general then and still achieve a non-trivial compression. And I should also say that the SDP for the operator norm is a rather nice one. So you get a solution. So for instance, in general, when you're solving SDPs and you want to say, oh, it's a nice SDP, you show that the solution has small rank or small trace norm. And this is all fulfilled here. So the solution for this, in this case, has trace 1, is of rank 1. And the value of this SDP scales like the square root of the dimension. So it's not too large, and you still cannot achieve a non-trivial compression in general. So we'll have to identify some extra assumptions which allow us to achieve a non-trivial compression. And as we'll see later, we'll have to make some assumptions on the matrices that define our constraints, not only on the solution itself. Okay, so as I said, maybe not all can be sketched. Okay, so the main technical tool we will need now to sketch the SDPs, where is our Johnson-Lindenstrauss transforms. What are these? These are just random matrices which, with high probability, preserve the scalar product between elements of some k element subset of RD or CD. So so what are we saying here? So the scalar product between vectors is essentially preserved up to this epsilon, okay? And the standard example, or maybe one of the standard examples, are IID Gaussian random matrices. So the entries of the matrix are IID Gaussians. And and D scales like epsilon to the -2, logarithm of k delta -1. So notice that we don't have any large D here. This only depends on how big your set is, which is k. And I must say that also this dependence on epsilon has been proven to be optimal, and this as well. And And however, this is again not, so this is the simplest case, but this is not what you would use in practice, and also for our things, because now, I mean, there's Johnson-Lindenstrauss transforms have been an area of very active research in the last years, and we now have sparser versions of this, of Johnson-Lindenstrauss transforms, which are much more useful in practice. But this is the somehow simplest example. Okay, so what can we do now with these Johnson-Lindenstrauss transforms? We can now get our positive maps, which approximately preserve our Hilbert-Schmidt scalar product. So if you're given some matrices Bi until Bm, and you're given some epsilon delta k Johnson-Lindenstrauss transform, where k is just the sum of the rank of all Bi, then you can show this bound over here. So this is essentially what we wanted, right? We have that the Hilbert-Schmidt scalar product is approximately preserved by this, and conjugation with Johnson-Lindenstrauss transform is clearly a positive, even completely positive map. So this is what we wanted. I should also say we were not the first to prove a statement of this form. So for instance, there's a paper by Harrow and others on model compression where they show this same bound. The proof is very simple, so I can quickly give you the proof. So let's fix some A and B. So can you read if I write down here? Yeah, okay. So fix two elements of this set, then you can just look at what, this thing is. And then you see this is just, sum ij, lambda I are the eigenvalues of A, mu j, and here you have, for the eigenvectors of AI, of I and B. This is what you get if you compute this trace. And then using the property that we have a Johnson-Lindenstrauss transform and picking our k element subset to be just the set of eigenvectors of A and B corresponding to non-zero eigenvalues, and using Cauchy-Schwarz, you get that this is smaller equal than this term is smaller equal 3 epsilon with probability at least 1 minus delta. And then if you use the triangle inequality, you get that the term up there is smaller or equal 3 epsilon sum of lambda I mu j, which is just 3 epsilon trace norm of A, trace norm of B. So you can see, it's very simple to prove this. The proof is admittedly very crude. You only need Cauchy-Schwarz and the triangle inequality. And I must say that this inequality is not as nice it's not exactly what we want. Why is that? Because the scaling with the one norm we have over here is not desirable. So, if we take MD with the Hilbert-Schmidt scalar product, just to be, if we look at this as a Hilbert space, and we just forget about positivity and use a normal Johnson-Lindenstrauss transform, then we would get a scaling with the true norm over here, which is much nicer because the true norm is easier to compute. It's also smaller than the one norm. So it would be much more desirable to have a 2 here, which is what you would get with the normal Johnson-Lindenstrauss. And as I said, I just used the triangle inequality and Cauchy-Schwarz. Maybe if one used fancier techniques or something you learned after the first semester, one could get a better bound here. However, we can also show that if you want this condition that the map you're applying to is also positive, then the scaling is not possible. So the scaling with the true norm is not possible. So if you want to have the scaling and you have at least d plus 1, so d is the big dimension, if you want this to hold for this many matrices, then the output of your the output dimension of your positive map has to be of the same order of your original dimension. So again, how do we prove this? Well, you can show that if you assume that a bound like this holds, then you get order large D positive semidefinite operators in this smaller matrix algebra here, whose Hilbert-Schmidt norm is 1, and their pairwise Hilbert-Schmidt scalar product is of order 1 over large D. And then you can show that this is only possible in spaces which have a dimension which is also of this order. Okay, so unfortunately, it doesn't seem like we can really improve the previous inequality. And maybe you would say, well, maybe you can improve it for low-rank matrices, but again, if you have a low-rank matrix, then the one norm and the true norm are not that different, so this would again not lead to a significant improvement. And one thing one could maybe try is to look at what happens if you only have a sublinear, if you only want this to hold for a sublinear number of matrices, and then you would also probably have a worse dependency on the probability of success. But yeah, so it seems like we cannot significantly improve the last inequality. Okay, so how do we use this bound on the Hilbert-Schmidt scalar product to now get our algorithm? So what are the assumptions we make? We assume we know something about the one norm of your target functional, so of your matrix A. We assume you know something about the one norm of the matrices that define your constraints, and also of some optimal point. And after this, so this is what we need for this technique to work. And then you start with your sketchable SDP, which is defined through the BIs and A. Now, what do you do to it? You just you pick your favorite Johnson-Lindenstrauss transform. You choose epsilon and delta as you please, and then you need to pick K such that it is larger than the rank of your optimal solution, of your target functional, and of the matrices that define your constraint. But I mean, you can always bound this by m plus 2 large D squared. And as we have this logarithmic dependency on k on the dimension, it doesn't really, you don't need a really good bound on k for this to work. And now you look at the following SDP of dimension small d. So what did we do? We just computed this conjugation with this Johnson-Lindenstrauss transform, and now looked at the SDP we get by having this different target functional and constraints. Now, the next step is to relax the constraints by just this term 3 epsilon norm of B1 plus times the 1 norm of your optimal solution. Why do we do that? Well, and you will call this now the sketched SDP. You will solve this, and this will now allow us to say something about the value of your original SDP. Why is that? Well, because of that inequality we just proved, by relaxing our constraints by this much, which is exactly what was our error term over there, our optimal point S x star S transpose is now feasible with probability at least 1 minus delta as we relax the constraints. And what happens for the value of this feasible point? Well, the value of this feasible point is given by this, but we have again a bound on this because of the theorem we proved, which is the following. But this term here, as this is an optimal point, is just the value of your original SDP. So from this, we get the following bound. So we cannot be sure that this point here is also the optimum of your smaller SDP. So it could be that this, as you take the maximum, this actually also increases, but you get this upper bound on the value of your SDP. Okay, so with this we clearly get upper bounds, and this is the statement of the theorem. So don't be too scared. It's a very long statement, but it's essentially what we just proved. That if you know the trace norm of your BIs, and you know you have a bound on the trace norm of some optimal point, then you get an upper bound of this form on the value of your SDP. Okay, so now a natural question to ask is, can it be the case that this actually explodes? So that this upper bound is a very bad upper bound, because again, there's no guarantee that this feasible point, which is given by the conjugation with the optimal point, will give you also something which is close to the optimum of your sketched SDP. And so whether this is the case or not depends on how stable your SDP is, as will hopefully be clear in the next slides. So what do we do now to show that the value of your SDP, of your sketched SDP, cannot explode? You take some optimal point y star of the sketched SDP, so of the smaller dimensional one, and we know that it then fulfills these constraints and optimizes this. Now, by cyclicity of the trace, if we just take this guy over here, and we know that this point, this positive semidefinite matrix, is a feasible point of this SDP over here. And the value of this feasible point is exactly the value of our sketched SDP. So, and this SDP we're looking at right now is just the perturbed version of your original SDP. So we just perturbed the original SDP by this much. So if the value of this perturbed SDP is not too different from the value of your original SDP, then the value of the sketch cannot be too far away from the value of the original problem, because it's a feasible point. So in particular, a lower bound to the value of this problem. Okay? So, and then we have a bound for, a continuity bound for general SDPs, but so you can find this in our paper. However, I must say it's quite messy, so the general case is quite messy, and I'll just comment on what you get for a particularly nice case in which you even get a feasible point of your original problem, which attains this lower bound. So what is this very nice case in which we can say a little bit more? So it's the case in which all the constraints are just 1. So just going back, so here instead of gamma I we just have 1. And you are given some kappa, which is just the maximum of your trace norms over here. And in this case, we can also show this lower bound over here to the value of your SDP. And we can also give you a feasible point which attains this lower bound. And again, the proof is quite simple. It's just the exploring the cyclicity of the trace again. So what will we do here? So when we look at the sketched SDP, we are just looking at constraints of the form S, Bi, S transpose, Y smaller equal 1 plus eta, because eta is exactly what we need to perturb our SDP with to get that to preserve feasibility. And now, I mean, we just again explore the cyclicity of the trace and get that for any feasible point, from any feasible point, we get a feasible point for the larger one. But instead of having a 1 here, we have this small perturbation. But we can just divide by this and then get that this is a feasible point of your original problem with this value. So in this very nice and simple case, we even get feasible points of your original problem whose value cannot be that far away from your optimal value. But as I said, we can also handle the general case, but it's much messier. Okay, so in summary, in this scenario, we get an upper bound on the value and a lower bound, and we also get a feasible point which attains this lower bound over here. So in this case, if this is well behaved and this is well behaved, then we can actually get a good approximation to the value of this SDP. Okay, so let's talk a little bit about the complexity gains from this algorithm. So if we assume that the one norm of your target matrix and of the matrices that define your constraints is of order 1, so does not scale with the dimension, and also the same for an optimal point. And we will now fix your error epsilon and the probability of failure delta and the precision zeta of until which you want to solve this SDP, then you need this many operations to solve your SDP. And this function here just tells you how many operations you need to solve an SDP with m constraints and of dimension d. So this is clearly, this term tells you how expensive it is to solve the sketched SDP, and this term here tells you how expensive it is to actually compute these matrices S, Pi, S transpose, which we need to solve the problem, or better, to state the sketched SDP. And we see that this is in general, the more expensive part of what we do. This is the main bottleneck. So as I said before, there are also sparse Johnson-Lindenstrauss transforms. So if the matrices that define your constraints are sparse, or you can also improve this term over here by exploring sparsity. So again, I refer you to the papers, to the exact bounds we get over here. But one should also say that, you know, computing these products can easily be parallelized. Yeah, so again, the main bottleneck is just computing these matrices as Pi, S transpose. And well, you know, again, if you fix all the parameters, we get some speedups, as long as, you know, solving the SDP directly takes at least longer than multiplying m d square, d large D matrices. And I should also say that throughout this talk, I implicitly assumed that the number of constraints you have is polynomial in the dimension. So if you again have an exponential number of constraints, then this won't work. And we clearly also need much less memory to solve these SDPs, because we are now working in a dimension which scales like this. So we can solve much larger instances of the problem. Okay, so just to finish, I would like to just give you a feeling of what you can do with this. So to be completely honest, we don't have a killer application yet. So if you think of, if you believe that your favorite SDP fits into this framework, please let us know. But we can do something with, for instance, this very simple problem over here. So we're given two observables, A and B, and we want to look at uncertainty relations of the following form. So we want to somehow get lower bounds on the variance of these two observables, and the expectation value is, and we want this to hold for states with, whose expectation value with respect to A and B lies in some interval. Okay, and this can, in finding the optimal C, can easily be cast as an SDP. Namely, you just look at this SDP over here, and yeah, this will give you the optimal C, so the optimal lower bound for this uncertainty relation. Now, we have a problem here, and this is again why I was talking before about the problem with the one norm, because this constraint here, which tells you that we're optimizing over all states, we cannot handle. Why? Well, the matrix Bi, which defines this, is the identity matrix. What's the trace norm? It's big D. So, and again, if we want to pick epsilon such that we have at least a constant error, we have to pick epsilon of order 1 over big D. The dependency on epsilon was quadratic, so we get a D squared they are in front of our in front of the dimension of our Johnson-Lindenstrauss transform. So we cannot handle a constraint like this one. So what do? We just drop it and look at what we get if we just, increase our feasible set by not only optimizing over states, but rather positive semidefinite matrices which satisfy these two constraints. And again, if the trace norm of B and A is of order 1, and their non-zero spectrum is not too wild, then we can also show the other assumption we need for this to work, for instance, which is that the trace norm of an optimal solution is also constant in the dimension, and then we have everything we need to apply our techniques to this problem. So just to do some numerics and show you what we can do with this, and let's take just AB of some fixed rank, and we say that the non-zero spectrum of A and B is just contained in some compact interval, which then gives you these assumptions. Okay, and then we just to show you some numerics. So in this case, so again, large D is the dimension of the original problem. Small d is then the dimension we chose for our Johnson-Lindenstrauss transform. And this is the value of the optimum C there. So not before we relax the constraints. And this is the error using our techniques. So with my computer, I can only solve this problem up to dimension 600 approximately. After this, I cannot do anything, but using our techniques, I can go up to dimension 4000. And you can see that it's much faster to just do this sketched version. It's always faster by almost an order of magnitude. The error we make is generally of a factor of 2. But again, the value of SDPs is rather small, so it's around 10 to the minus 2, right? So to get this precise Johnson-Lindenstrauss transforms, we would also have to go through much larger dimensions, which again, I cannot do on my laptop. So, and with this, I would like to thank you for your attention.
Thank you.